All right, welcome back for part 2. Here we go. Last lesson. Watch this, though. Watch how good I am at the smartboard now. Watch. Ooh, cool. Yeah, not that cool. What's going to happen is we got about, I think it's 4 or 5 examples maybe, and each of them has strategies that you actually did in the activity yesterday. The expectation, solve quadratic trig equations using various strategies. Well, one of them is a common factor. And notice that right now, the way it looks, I can't use a common factor because there aren't any common factors. And in fact, you might be tempted to divide by tan x, right? Ah, bang, bang, gone. Well, the thing is, you can't divide by an expression like that in an equation because you might be dividing by 0. And dividing by 0 is kind of an illegal math thing to do. And in fact, as it turns out, when tan x is equal to 0, there's some solutions here. So that's a bad thing to do. Same thing last day when we were doing that equation, we couldn't divide by x because we would be dividing by 0. So what's the strategy? Well, when we want a factor, we have to have one side equal to 0. So I'm going to get the tan x on the other side. And then you see there's the common factor that I was talking about. So I get tan x out front. What am I left with? Cos squared x minus 1 equals 0. So here I got, again, 2 trig equations. I have tan x equals 0 and cos squared x minus 1 equals 0, right? Two equations. And I'm going to solve them. How we solve this one, the tan x equals 0, there's a number of ways to solve it. You should recognize that this is a special angle. And it doesn't matter how you solve it. One thing you got to be careful about, if you use your calculator, you're going to miss some solutions. Remember, there's lots of solutions to these equations. Usually, when we're solving equations, we got to draw some sort of diagram. And in fact, if you remember your tan graph, you don't remember your tan graph? There are asymptotes starting at pi over 2 and then every pi, and tan x is always increasing like this. And in fact, we get 3 solutions. We get x equals 0, x equals pi, and x equals 2 pi. 3 solutions. Another way that you could have solved that is by changing this to sines and coses. And of course, you don't have to have every way down, but I want to mention it just because if it was your instinct to think of that equation as this equation, and then wondering when this equation is equal to 0 is when sine x equals 0, right? So when is sine x equal to 0? Yeah, same spots, okay? So it's kind of a sloppy version, but anyway, we get those 3 solutions. What about this one? When is this true? This actually, believe it or not, is also a quadratic trig equation. This kind of looks like this, doesn't it? And I could factor this into cos x minus 1 and cos x plus 1, right? This is a difference of squares. In this case, I've thought of A as cos x. And of course, you don't have to worry about this, solve a simpler problem if this makes complete sense to you. And then I can solve these 2 equations. Cos x equals 1 and cos x equals minus 1. So where are these things true? Well, you might think of the graph again, or you could think of the rotation angle, or you could think of this any number of ways. That's up to you. Cos x kind of looks like that. There's pi. There's 2 pi. This is y equals cos x. Draw a diagram. When is equal to 1? At x equals 0 and 2 pi. And it's equal to negative 1 here. X equals pi. So notice if I collect up the solutions, they're actually copies of the same solutions. So, and notice that these solutions will happen every pi. So if I wanted all of the solutions, It's just, well, how am I going to write that? 0 plus pi n, or just pi n, right? Where n is any integer. Any multiple of pi, I'm going to get a solution. The principal solutions are the ones we found. Principal solutions. 0, pi, and 2 pi. Okay, dandy. There's lots of ways to solve these perfect ones, by the way. The most dangerous might be using your calculator because you'll forget the second solution, so be careful there. You ready for some more groovy graphics here? Ooh, let's do that again. One more. That's awesome. Okay, anyway, what is the strategy? Trinomial factor. What the heck's that? Well, remember, a trinomial is, back in grade 10, it was this thing, right? ax squared plus bx plus c. That's what a trinomial is. This means, and this factors into two factors like that, right? So they're saying that this kind of looks like this. Specifically, what does it look like? Specifically, this looks like a trinomial 3a squared minus a minus 2, right? And this is what I kind of think. I don't have to do it like this. And if notice, if it helps you to do a substitution where I think of a as sine x like this, we've seen this strategy before at times, then go right ahead and do that. Do this factoring off in the side. Right? What is this factoring? Well, this is a hard trinomial, and some people use the box method, and some people use the decomposition, breaking down the middle is what Miss Lichty used to call it. This one, the numbers are small enough, so I think you can use trial and error. I got to figure out where the 2 goes. Does it go here or here? So that when I multiply it back out, I get a minus 1 in the middle. Notice if I put the 2 over there, I'd have 3 times 2 would be 6, and that's no good. So the 2 is going to have to be there. The 1 goes there. Now I just got to figure out the signs that makes it negative 1. Notice positive 3 and negative 2, that's the wrong way. So this is going to be positive 2 and minus 3, right? So when I multiply it out, this works. And some people, by the way, this factoring is kind of difficult, but practice it. Some people will be able to skip and be able to see this as the trig factoring right away. They won't have to worry about this a business. This is completely optional and helpful for the folks that wouldn't be able to skip to this step right here, where a is sine x plus 2 and sine x minus 1 equals 0. And then again, this gives me 2 linear trig equations. The idea of 2 linear trig equations multiplied gives me the quadratic equation. Now I'm off to the races again, right? Equals 0, and I get sine x minus 1 equals 0. This is one of those special ones again. Oops. Sine x equals 1. And again, how are you going to solve that? That's up to you. I could use the graph, right? I could use the graph if you want. I haven't talked about the rotation angles for a little bit. So if I think of the rotation angle here, when is the y coordinate? Remember that sine is the y coordinate. When is the y coordinate equal to 1? Right? This is the y coordinate equal to 1. When is the y coordinate equal to 1? Right there at 0, 1, and that's a rotation angle of x equals pi over 2. And I could have got that same thing from the graph. That's an easy one, right? Special angle, one solution. I suppose I could put the plus 2 pi n there to get all solutions, but that's the principal solution. How do I deal with this other one over here? Well, I've got to solve for the sine x, so it looks like a grade 11 equation, minus 2 over 3. And this is like a regular one. This isn't a special angle. There's no square roots of 3's. There's no halves. So this is a diagram calculator think question. What do I mean diagram? Well, I think this is what I would do. Diagram, rotation angle. I either think where is the sine negative, or I think of again, rotation angle. When is the y-coordinate equal to negative 2/3? Well, this is the y-coordinate of negative 2/3 is about there. So I can see my two solutions are here and here. And then there's my related acute angle. I'm calling that alpha this time. And then I can, once I got my diagram, I can use my calculator to figure this out. Dandy. So I'm going to put into my calculator, I'm going to put in x equals sine of -1 of negative 2/3. Oh, by the way, and I kind of goofed this up, but here are my two solutions, right? My two principal solutions. There's kind of like my x1, and there's my x2. And I'm putting this into my calculator, and I got to think about what the calculator is going to give to me, right? So I jam that into my calculator in radian mode, and I get the calculator gives to me x equals negative 0.73. And try that, and that's radian. So what is that given to me? That's this angle, isn't it? It's given me that angle. So therefore, I can say my related acute angle is alpha is 0.73, the positive, right? It gave me the negative. I don't want the negative because the negative one isn't the principal solution, so I'm going to take the related acute angle of 0.73. Notice a textbook, how our text does this is they never put in a negative here. They always put in the acute angle, and they always get the related acute angle. So they'd always just put in this, and that's a fine way to do that, right? And then you can adjust from there. That's a kind of a little bit of a change between the way I present things in the textbook, and you're welcome to try that. All right, so what are my solutions then? I got my x1 is this angle here, okay, which is pi plus the related acute angle is 0.73. And again, if I had a period change or something else, that's when I put in the plus 2 pi in, but this doesn't, so I'm leaving it just like this. Jam that into a calculator, I get 3.87. And again, use the pi button on your calculator. You're not using 3.14. Use the pi button. Dandy. X2 is almost all the way around. It's actually the one that's coterminal with what our calculator gave to us. That is 2 pi, subtract the related acute angle, right? 2 pi is all the way around, subtract the related acute angle, and I get that's equal to about 5.55. Again, 2 times pi, hit your pi button, subtract 0.73, and now let's collect up all the solutions. And these are the principal solutions. Even though I could have a whole bunch of solutions in general, the principal solutions are 3.87, 5.55, and from the first one, let's not forget, pi over 2. Dandy. Okay, I think I'm going to pause there. This feels like it's almost time for a pause. Yeah, 13 minutes, and we're into the dreaded part 3. This might go into part 4. I don't know. Let's hope not.